Hello dear students, today we are going to start with the chapter of inorganic chemistry, the D and F block elements. This is a very logical chapter. What type of questions you can expect from this chapter? Give reason questions, complete the equation type of questions, then graph based questions and structure of the compounds. So these are the questions which are asked in your board exams from the chapter the D and F block elements. First of all, let us discuss why the name D block element is given to them. The name D block element is given to them because in this the electrons are added in penultimate shell. That is, I will say, second last shell, N-1D. In this shell, electrons are added and therefore the name is given D block elements. What is the position of D block in the periodic table? This is D block and it is sandwiched between S block and P block. The F block is written separately. Now we know all the elements present in S block, they are most electropositive, or I will say they are metallic in nature. Whereas all the elements of P block, they are most electronegative, or I will say they are non-metallic in nature. D block represents the transition from most electropositive to most electronegative, or I will say D block represents the transition from metallic character to non-metallic character, and therefore D block element is also given another name, transition elements. Clear to you? Now what is the main condition for D block element? For any element to be placed in D block, the main condition is that they should have partially filled D orbital, or I will say incompletely filled D orbital. Then only we can say it is an element of D block. If the D block is completely filled or if it is vacant, then it will not be element of D block element. Based on this condition, there can be some good questions in your board exams. Let us have a look on all the elements of D block. So this table represents D block elements. As you people can see, D block comprises of group 3 to group 12. D block starts from period number 4. So N equals to 4, 5, 6 and 7. So D block represents from N equals to 4 to N equals to 7. As I told you just now that in these elements the electrons are added in penultimate shell, and therefore in this N equals to 4, so electrons will be added in 3D first and then 4s. For the second one, it will be 4D 5s. Similarly for third one, 5D 6s, and the last one 6D 7s. Therefore, the first row is called as first transition series. The second row is called as a second transition series. The third row, it is called as third transition series. And the last one, it is called as fourth transition series. There are so many interesting things in this D block. As we can see in this table, there are total 40 elements in this. But actual transition elements, they are only 36. Okay, 4 elements, although they are placed in D block, but they are not considered as transition elements. Which are those elements that we'll be discussing in this topic itself. But before that, some interesting thing regarding these D block elements. I will tell you the tricks to remember first, second, third transition series. The first one, listen to me very carefully. The first one, Sachin Tendulkar, very crazy man, free coaching to Nitin's cousin. Again I am repeating. Sachin Tendulkar, very crazy man, free coaching to Nitin's cousin. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Especially first transition element must be learnt by heart by you people. Okay, coming to the second one. Yari zara nibha mot tak ruh, sorry it is रुख राह पड़े आग में कूद. Again I will repeat. यारी जरा सी निभा मौत तक रुके राह पड़े आग में कूद. Second transition series. Moving on to the third one. ला हफ्ता वरना रे ओसामा इधर पिटाई और होगी. ला हफ्ता वरना रे ओसामा इधर पिटाई और होगी. So using these three sentences, using these three tricks, you can easily remember first, second and third transition series. Especially first transition series must be learned by you people. Okay, why we focus so much on D block elements? Because there is a variety of elements in this table. For example, these elements, nickel, palladium and platinum. These are used for hydrogenation. In your lower classes, you have studied that hydrogenation requires catalysts, and these catalysts are generally nickel, palladium and platinum. Similarly, iron is also used as a catalyst in Haber's process. Iron is used as catalyst in Haber's process. Vanadium in the form of V2O5. It is used as catalyst for contact process. Getting me? The other elements like copper, silver and gold. These are called as coinage metals. Because in ancient time, coins were made of copper, silver and gold, and therefore they are called as coinage metals. Now I told you that there are 4 elements which are placed in D block, but they are not actually transition elements. These are zinc, cadmium, mercury and UUB. These one, they are called as pseudo transition element. Why? Because they do not show incompletely filled d orbital either in their ground state or in their excited state, and therefore these 4 are not considered as transition element. Instead we'll call it as transition element. So these are not transition elements. Then metals like platinum, silver, gold and mercury, these 4 metals, they are called as noble metals because they hardly react with any other metal or any other element, and therefore they are called as noble metals. Elements like iridium and osmium, they have highest density of the periodic table, most dense elements, as well as osmium is the only metal which can show +8 oxidation state. So there is so much of variety in D block elements, and therefore D block elements becomes the most interesting one. We have to study the trends of D block elements. So we will begin with the trends. The first trend that we are going to discuss is electronic configuration. The general electronic configuration of D block elements is n-1 D 1 to 10 ns 1 to 2. Very interesting one. Again I am repeating the concept that D block element must have partially filled or half filled or incomplete filled d orbital either in ground state or excited state. Even if it is in excited state, incomplete orbital, d orbital, then it will be called as a element of D block. Okay. Now n-1 D 1 to 10 ns 1 to 2. This is the general electronic configuration. There are exceptions. First one, like chromium. Chromium atomic number is 24. So ideally its configuration should be 3d4 4s2. But this is not the condition. Chromium with atomic number 24 shows electronic configuration 3d5 4s1. Our first point. Secondly, copper with atomic number 29 should actually show the configuration 3d9 4s2, but it do not. Instead, it shows the exceptional configuration 3d10 4s1. These two are exceptional cases. Now, why chromium and copper do not follows the general electronic configuration and shows the deviation from it? Look at the configuration. In this, it shows half-filled d orbital and completely filled d orbital respectively. Half-filled d orbital for chromium and completely filled d orbital for copper. We know half-filled or completely orbitals, these are extra stable. And therefore chromium and copper shows exceptional case. They show the configuration 3d5 4s1 and 3d10 4s1 instead of 3d4 4s2 and 3d9 4s2. The next exception is zinc, cadmium and mercury. They shows the electronic configuration 3d10 4s2, 4d10 5s2, 5d10 6s2. So actually they are following the general electronic configuration, but these are not transition elements. Very interesting thing, and this is a important exception. All the exceptions which I am going to discuss today, they are all important one. So why zinc, cadmium and mercury, they are not considered as transition elements? Because their d orbital is completely filled in ground state as well as excited state, or I will say in their oxidation state. And therefore they are not transition elements. For transition elements, what is the condition? Partially filled or incompletely filled D, either in ground state or in excited state. Like zinc. Zinc in +2 will show configuration 3d10, which is a completely filled d orbital, and therefore it is not a transition element. Similar is for cadmium and similar is for mercury. Next exception is of silver. Silver shows electronic configuration 4d10 5s1. Now d orbital is completely filled. Actually it should not be a transition element, but if we consider the compounds like silver oxide, silver fluoride, in these compounds silver is in +2 oxidation state. In +2 oxidation state, The electronic configuration of silver is 3d9, that is incompletely filled, incomplete d orbital, and since it satisfies the condition that the d orbital should be incompletely filled, and therefore silver is considered as a transition element. Very interesting one. Next trend is atomic radii. I will explain it with the help of first transition series. Now what we have studied in our 11th class, that as we move from left to right, actually what happens? The atomic radii decreases. This is what we have studied in class 11. So till I will say manganese, it follows the trend. Till manganese, I will say the atomic radii decreases as there is increase in atomic number. But onwards from manganese, iron, cobalt and nickel, here the atomic radii becomes near about constant, near about 125 picometer. And again when we move to last, copper and zinc, here the atomic radii increases. In that also I will say the atomic radii of zinc is greater than that of copper. Now why there are so many variations in atomic radii? For explaining this variation in atomic radii, I will consider two factors. One is a screening effect and another is effective nuclear charge. Now based on this I can explain the variation of atomic radii. For the elements scandium to let's say manganese, effective nuclear charge, this factor is dominant. And therefore it will follow the normal trend that the atomic radii decreases. But as we reach to the middle of transition series, where the number of d electron in penultimate shell starts increasing, then the changes start occurring. So iron, cobalt and nickel, in this case the effective nuclear charge is near about same to that of screening effect, and therefore the atomic radii is near about constant. Whereas in case of copper and zinc, screening effect is dominant over effective nuclear charge, and therefore their atomic radii increases. Or I will say the number of d electrons increases in copper and zinc, and therefore their atomic radii increases. Now coming to this point, I told you that atomic radii of zinc is greater than copper. Why? Because the zinc shows the configuration 3d10, 5s2. So it has completely filled d orbital, and therefore the electron repulsion increases. And therefore electron repulsion increases. It will impact on the atomic size, therefore atomic radii will also increase. So what we have seen at the starting of the first transition series, it follows the normal trend that atomic radii decreases with increase in atomic number, but when we come to the middle of the transition series, then atomic radii becomes near about constant, and when we reach to the end of the period, here we are discussing n equal to 4. We are discussing about fourth period. When we reach to the end of the period, suddenly the atomic size increases due to electron repulsion in d orbital. Now one interesting thing about iron, cobalt and nickel. Iron, cobalt and nickel, these make Dauber-Near triad. This question is asked in JE, and the students remember only the common one. This answer is rarely known by the student. Okay, now this whole concept of atomic radii and its variations, I will explain you with the help of a graph. This graph shows the trend in atomic radii, and this graph is asked in board exams also. So the first one, this is the first transition series, scandium, titanium, vanadium, chromium, the atomic radii decreases, the normal trend. Then till nickel it becomes almost constant, and for copper and zinc it increases, and zinc will show again higher atomic radii than that of copper. So this was for first transition series. Okay. Now for second and third transition series, this one from ytterbium. This is a second transition series graph. And for lanthanum, this is a third transition series graph. They will also follow the same trend. First of all, normal decrease, then near about constant, and then increase. But the interesting thing, you can see that first and second transition series, their graph, these lines are coinciding. That means the size of second transition series and third transition series is almost same. This is a very interesting case, that size of atomic radii of second transition series and that of third transition series is almost same. The reason is explained by a phenomena called as decontraction, or we can also call it as lanthanoid contraction. About this we'll be studying in detail in F block element. So you have to remember this graph, and based on this graph lot of questions can be asked. Remember always first decrease near about constant and then increase for first transition element, and for second and third transition series what you have to remember, the trend is same but their size is almost same because of lanthanoid contraction. So today we have seen the general introduction of D block elements. We have seen the trends like electronic configuration and atomic radii. So based on this, try to solve some questions on your own. Based on today's module, try to solve these give reason question. From D block elements, maximum give reason questions are asked. Now especially for the second question, I will give you a hint. Copper is regarded as transition element although it has a completely filled d orbital. Why? For this, think of its oxidation state copper plus 2. What will be its electronic configuration in this oxidation state, and you will get the answer. Thanks for watching. Have a nice day.